I have some dice, but not just any dice. With these intransitive dice, I will demonstrate a paradox of probability, I'll show that democracy is impossible, and I'll win a game of chance against a child. So let's go.
I'm almost sure.
Welcome to Almost Sure. Yes, the dice. They are regular in as much as they are six-sided, but if you look closely at them, then you will see, for example, this one has 6 on this side and it's got 6 on that side. If you were to look at this dice, you see it's got some zeros on it. And this dice has got 3 on every side. If I'm to put them down in order, so blue, orange, red, green. Then if you were to play red against green, see which rolls the highest score, then red beats green. Most of the time, it gets the higher score. That happens 2/3 or 67% of the time. In a similar way, orange beats red and blue beats orange. So it looks like blue is the best here and green is the worst. If I was to play blue against green, then surely blue would win. Most of the time. In fact, that's wrong. And green will beat blue 2/3 or 67% of the time. If we're to play a game with these dice between 2 players, simply see who can roll the highest score, then paradoxically, the player who gets to choose their dice first is at a disadvantage, because the next player can always choose a dice that performs better. In fact, the Sage of Omaha, Warren Buffett, was apparently a fan of these dice and once challenged Bill Gates to a game. Well, now it's my turn. I'm going to need a challenger, a worthy opponent in this game of chance that's rigged in my favour. But who can play me? Maybe somebody in the comments down below if you want to challenge me to a game.
Me!
Oh, hello.
Hey.
Welcome to Hayley here. You want to play this dice game?
Yes.
Okay, it's the simplest game in the world. What we do is we both choose a dice, we roll it, whoever gets the highest score wins. And we're going to roll into this square here, and we will repeat this several times to see who's the overall winner. Pick your dice there, Hayley.
Pick green.
You're picking green, so I'm picking red. Let's go. You win. So that's 26 to me and 21 to Hayley. I'm the winner. Actually, it's a little closer than I was expecting, but that's the nature of a random game. Do you want to play again, Hayley?
Yes.
Okay.
You choose the dice first.
Oh, okay. Well, I suppose I will pick red. And the winner is Hayley. You played a good game, Hayley. Well done. Let's put the dice to one side for a moment. Generally, when we have to make a choice between 2 options, then comparing one against the other, we can maybe say which is the best choice. And this will lead to an ordering between them with best and worst options. maybe A is better than B and B is better than C. But this ordering goes wrong if then C is better than A. There's no best or worst. And we say that this is non-transitive or intransitive. It's like the popular game. Scissors beats paper beats rock, which beats scissors. But that's an artificial construction. What if the options are represented by numbers? And the biggest number wins. Then there is a best and a worst option. But random numbers are different. The outcome of a comparison with random numbers will be random. So we can say that A is better than B if it's bigger more than 50% of the time. But now we can have a cyclic arrangement where each option is better than the next. Intransitivity, like this, is what we saw with Efron's dice. But this is actually quite common, and that shouldn't surprise a mathematician. There's no natural complete ordering on random variables. Non-transitivity does lead to a scenario which, quite frankly, is just weird. If you have to choose one of A, B or C, then let's suppose you go with B. But what happens if option C is taken away? Logically, A beats B, you should change your mind and go with A instead. So adding or taking away an option that you are not going to choose either way changes which one of the other two you pick. Here's an example which I came across coincidentally while preparing the previous video. Choose a sequence of 2 coin tosses. Then toss a coin repeatedly until this sequence comes up. And if we have 2 players each choosing a sequence, then we can say that the winner is the one whose sequence appears first with consecutive tosses. For example, which is more likely to happen first, heads tails or heads heads? Well, that one's easy and they're both equal. You just need to wait for the first head to appear and then the very next toss will determine the winner with 50% chance for each. But what about tails heads versus heads heads? Now, this sounds similar. I just switched the order of the tails heads around, but it's not. The only way that heads heads can win this one is if both of the first 2 tosses are heads. Just think about this. If one of them was a tail, then we just need to wait for the next head to come up after this, and that's necessarily tails heads, and it will be the first tails heads and it wins. But the first 2 tosses being heads has only got a probability of 1 in 4, so tails heads has a 3 in 4 chance of winning, or is 3 times as likely. So we see tails heads beats heads heads, and this is equal with heads tails, and heads tails similarly will beat tails tails, which is equal with tails heads, as shown here. And the 3 means that tails heads is 3 times as likely as heads heads. Now this is a cycle, so it's intransitive. Well, it's nearly intransitive. Some of the choices are equal, so it's a kind of weak type of intransitivity. But if we instead look for sequences of 3 coin flips rather than 2, and we compare them, then we get this. Now there are cycles, and this is intransitive. For example, tails heads heads beats heads heads tails beats heads tails tails, which beats tails tails heads, and then that loops around to beat tails heads heads. Regardless of which sequence the first player chooses, the second can always choose one that beats it most of the time. And this game, with tossing coins and waiting for some consecutive sequence of 3 tosses, this is called pennies game. Not because you can play with pennies, its inventor is Walter Penny. In fact, given any sequence, the one beating it can be constructed by taking the first 2 and shift them to the end, and then you add a heads or tails at the start, whichever one makes it different from the middle of the sequence. So for example, tails, heads, heads is going to be beaten by tails, tails, heads, like so. And if you watch my previous video on martingales and optional sampling, then maybe you can see why this works. In fact, maybe you can use martingales to compute all these displayed probabilities and the missing comparisons too. Can you give a general formula which, given any two finite sequences of heads and tails, tells you the probabilities for which appears first? Now, it's not difficult to artificially construct non-transitive games. All we need to do is, well, let's consider three choices, A, B, and C, and then we will assign them possible scores. Let's say they get scores 3, 2, 1. So A scores 3 and C scores 1. Or we can do it 2, 1, 3 in order, or 1, 3, 2. And if these three scorings are each selected with equal probability, then we see that A beats B 2/3 of the time, and B beats C 2/3 of the time, C beats A, all with 2/3 probability. So we get a simple construction of a non-transitive game. With dice, non-transitivity is more surprising because the scores on each dice is independent. Let's look at Efron's dice a bit more closely. Listed like this, each beats the next 2 times out of 3. Maybe it's easier to see that each loses to the next 1 time out of 3. So we see that blue loses to orange whenever orange rolls 6, which is 2 out of the 6 sides. Orange loses to red in these cases, which is 4 times 3 or 12 out of the 36 possible outcomes, and so on with the other comparisons. I also like to draw it like this. Each dice is represented by a number line, with a dot for each possible outcome labelled by its probability. Then the probability of each dice losing to the next one is just the product of two probabilities, like this.
Can it be done with only 3 dice?
Just remove the red dice, and they're still intransitive. Blue beats orange, beats green, beats blue. Orange only beats green with probability 5/9 though. There are sets of 3 non-transitive dice where each beats the next with probability 7/12 or more, but we can't get to 2/3 probability like with Efron's dice, so it's not quite as good. But how non-transitive can we get? Maybe we can do better than the 2/3 probability with Efron's dice. What about if we have more? More dice, maybe we can get higher probability. Actually, no, we can't. Efron's dice are the best possible. At least it is for regular 6-sided cubical dice. This is not difficult to prove. Just list the sides in increasing order, like I did here. Look at the number in the 3rd position. As we go round the cycle, this ends up back where it started, so it can't decrease at each step. Any time that the number increases, or stays the same, which it must happen at least once as we go round, then take these 2 dice where it increases. If the first dice, any of the first 3 sides are rolled, and on the second dice, any one of the last 4 sides are rolled, then our dice loses to the next one. And this is probability 3 times 4 out of the 36 possibilities, giving at least a 1 in 3 chance of the first dice losing to the next, so no more than 2/3 chance of winning, just like in Efron's dice.
How about dice with more than 6 sides?
Now this is not obvious. Maybe you think that with enough dice and enough sides we can get close to each one beating the next with near certainty. It would seem to be a natural limit case, but no, that's wrong. In fact, I asked this on Twitter with 3 options, plus show the results, and fewer than 6% of votes got the correct answer. For random variables x1 up to xn, it's impossible, as we go round the cycle, for each one to be greater than the next with probability 75% or more. To see why, look at the medians. As we go round, then we end up back where we start, so the median can't decrease each time. And at any step, if the median m of xi is less than or equal to the median of xi plus 1, then the probability that xi is less than or equal to xi plus 1 is bounded below by the probability that xi is less than or equal to m multiplied by the probability that m is less than or equal to xi plus 1, which by the definition of the median, this is bounded by a half times a half or a quarter. In fact, you can see this inequality will be strict, so the probability that xi is greater than xi plus 1 has to be less than 3/4. But if we choose a probability p less than 75%, is it always possible to construct an example where the probabilities all exceed this, where every dice has probability p or more of exceeding the value of the next one as we go round a cycle? Yes, it is, if we have general n-sided dice. But rather than trying to explain this verbally, here's an animation of the construction. Each random variable will be greater than the following one with probability at least 73%. Our first random variable will just take a single value, so it's deterministic, and all of the other random variables will take 2 values. Be updating our probabilities using this blue curve. We need to show that it lies below the red line of y equals x. Now that's done, let's take it away and generate our sequence. Finally, we have a probability less than q, meaning that we can complete the cycle and we have our non-transitive example, which we see in this case with p equals 73% took 10 random variables. Suppose that there's an election with 4 people running for office: the blue candidate, the orange candidate, the red and the green, represented by each of these dice. In fact, with these colours in the UK, it could be Conservative, Liberal, Democrat, Labour and Green, but I won't use these examples. In fact, let's get rid of the red dice just to keep it simple. We know that these 3 are still non-transitive. Let's say blue is B for Boudica. She'll take the fight to the Romans. And orange is Olaf, the Viking king, and green is Genghis Khan. Rolling the dice will give us a score that a randomly selected voter assigns to each. Let's just assume that it's distributed this way. And the voter will vote for whoever they score the highest. In that case, Genghis Khan would win with 4/9 of the vote, with Olaf coming in second and Boudica coming in last with only 2/9 of the vote. But hang on a moment, should Genghis really win? I mean, most voters prefer Olaf over him. So maybe Olaf should be the winner. But then most voters prefer Boudica over Olaf. So maybe Boudica. But then most voters prefer Genghis over Boudica. So no matter who is awarded the win here, one of the other candidates is preferred by most voters, which is a bit strange. It's kind of paradoxical and rather unfortunate for the idea of democracy. There's no good way of picking a winner that people will agree with. We don't really need dice for this example. Let's go back to the previous example of non-transitivity. In the order of the candidates, let's suppose a third of people assign them scores 3, 2, 1. A third assign 2, 1, 3. And a third assign 1, 3, 2. Then no matter who is awarded victory here, there's going to be one other candidate that 2/3 of people prefer. This is called Condorcet's paradox, after the Marquis de Condorcet. You have to excuse my French pronunciations here, who discovered it in the late 18th century. Even if candidate A is preferred over B, then the introduction of a third candidate could cause B to win. There's been many failed attempts to design voting systems which avoid these issues, but this culminates in Arrow's famous impossibility theorem, which takes it even further. If voters rank all available candidates, then we would like to combine these into an overall ranking. But not just any old ranking, it must respect the wishes of the people. If everyone ranks candidate A above B, then the overall ranking should put A above B. I mean, that's pretty obvious. And we also shouldn't just rank them according to what a single voter says. Effectively, that's just making him a dictator. And then finally, whether or not A is ranked above B shouldn't depend on how a third candidate is ranked. And this is the problem that we saw, where the introduction of a third losing candidate changes who is elected between the leading two. Arrow's theorem is that this is impossible. It's not possible to design a voting system which respects these simple requirements. I'm not going to go into the details here, maybe it's a subject for a later video. Let me know in the comments if this is something you would like to see. Either way, please like and subscribe. I'm going to go away now and try and make my videos better each time, even if that doesn't mean they're any better than my first one.